Okay, well, good morning, everybody. Good afternoon, whatever. This is a talk on photometric products. I was asked to talk about photometry. So things like interesting questions like deblending, astrometry, databases are more or less out of scope, except where I felt they were necessary to discuss in the context of measuring fluxes of objects. Okay, so I'm going to cover photometry, point sources, and galaxies. I'm going to talk about the photometric calibration, which is a little tricky if you want to get below about 1%. There are a couple of documents that are useful. One is the DPDD, and when you get the slides, you'll see that that's a link in an elegant dark blue color. There's also a somewhat dump of content, the Data Management Science Pipeline Design, LDM 151, which has more information at a somewhat uneven level. Now, there are many subtleties in making these measurements because the data we're dealing with is and or will be subtle. So the actual state of the LSST DRP, that's the data release processing, which is what I'm talking about today. I'm not talking about the transient photometry almost entirely, is well summarized in this paper by Jim Kuhn. That's also a link. And that's based on experience processing about 150,000 CCD images from HyperSupremeCam. In addition to the deep drilling fields, the deep drilling field in Cosmos goes to something now like 30-year LSST depth. We haven't put all that data out, but some of the problems we've come across are at 27th magnitude, which is significantly deep, in fact, qualitatively different than things like Sloan or DARES or kind of stuff. Okay, so photometry. Now, what we want to know is how many counts there are in the object. Now, I'm not going to talk about magnitudes here. In fact, LSST is, I think, going to be used in nanojansky as a linear flux unit. But if I say magnitude, think flux, and don't worry about the logarithms and the 2.5 over log e I pi's and things like that. Okay, so I'm going to assume that we've run a deblender. I think Peter Melchior is going to talk to this group about a deblender in a few weeks. It's a fascinating and impossible problem, but I'm not going to talk about it today. So I'm going to assume that we've reduced the problem to measuring isolated objects. That's an extremely bad approximation, but a good deblender gets you close to it. It's not a trivial operation. Now, some of the measurements I'm going to talk about will be better made as part of a simultaneous fit during the deblending. I'm just not talking about that approach to doing things. That's the way, for example, that Dustin Lang and David Hogg have been pushing, making some measurements. And I think the jury is still out to what extent you do better for a particular science case to do a simultaneous naive fit to a bunch of components, and to which you do better to try to identify components and then measure them. For example, if you want to measure a Gini index for a well-resolved galaxy, I don't think model fitting will work very well. If you want to measure shapes, perhaps it does. Okay. Next, sky subtraction. I'm not going to talk about sky subtraction, at least not very much, because the assumption is that we've got rid of it. But unfortunately, exactly how we do the sky subtraction is going to mess up the flux of extended objects. One of the more embarrassing things in my Sloan pipeline was that the decisions taken on sky subtraction significantly affected fluxes of objects that Jim Gunn and I thought were going to be unaffected. And that's a mistake. It was my mistake, but it really matters. So just to get you on the LSST page, we expect to measure the sky on arbitrarily large scales. In fact, we did some experiments on that with Yusra, who's I think on the line with the University of Washington. We have a scheme for how to do that. In particular, that means on scales large compared to a CCD. And the LSST CCD is 13.6 arc minutes on a side. Incidentally, that's exactly the same width as a Sloan CCD image, but that's because the CCDs are bigger with smaller pixels. Okay, we will explicitly remove power on large scales. People always remove power from objects on large scales. They normally do it by saying, 100 pixels is big enough, I think. I'm planning to do that explicitly. Examples would be the wings of bright stars. Nobody cares about the wings of bright stars. That's fine. That's unambiguously a good idea. Again, it's not totally trivial, but I think it's doable with the catalogs like Gaia. We will remove the extended light from large enough galaxies and clusters of galaxies. I'm particularly thinking of ICL in clusters and tidal features in galaxies in some well-defined way. And we will make it possible to return that data to you. The problem here is that if you include M31, say, M31 is of course not really something I'm worrying about, but very large galaxies indeed, they essentially say the whole field of the LSST is a blend, or intercluster light from Virgo or something like that. So you have to do something, but we will remove that in a way that isn't just magic, and we will tell you something about what we've taken out and tell you how to put it back in. And I'm thinking of something like a wavelet decomposition, a translationally invariant wavelet decomposition on scales above X arc minutes. But we certainly have not done that yet. One of the things we've just been discovering in the deep HSC data, 3, 4, 5 hours per band on Subaru, is that we're coming into the limit that the wings of galaxies are really significantly causing troubles for blending the whole frame up. And then finally, we have to remember there are things like IR cirrus. Nobody except Bruce Strain cares about IR cirrus, but it does scatter light back into the beam, so you get a background. We need to remove that background, and exactly how you do that without compromising your galaxy photometry is an interesting challenge. I don't think it's a possibility to do it right at all in all fields, but at the very least, I will give you a model of what we did. Okay.
Robert, did you define the large scales as excess of 100 pixels? I've taken some notes.
No, it'll be much larger than that. I don't know how large yet.
Okay.
It'll be on large. I don't know how large it'll have to go out to be. It'll be on scales of many thousands of pixels, I'm hoping. Certainly thousands of pixels. So that's 200 arc seconds, so 3 minutes.
Thank you.
But again, that's not yet clear, but we will not just, as one traditionally does, do sky subtraction per CCD, and then all that power is gone, right? We're not planning to do that. So I'm not planning to use local sky estimates. Now, that'll surprise those of you who do stellar photometry, where you often do that. The experience from high galactic field surveys like Hypersupreme Cam or Sloan for that matter, is that you don't need to do that. The width of the stellar locus, the GRI locus, the blue part of that in HSC processing is now about 20 millimagnitudes. Some of that's due to filter problems, some of that's due to the intrinsic width. So we can certainly get down sort of 1% errors without doing a local sky subtraction. In sufficiently dense regions, we may need to reconsider this. Where we've given up on galaxy photometry, you may need to do something more local, but we can't do that for galaxies. So the going in position is that we will not do a local sky subtraction. I don't believe we will need to. I don't think it'll compromise the stellar photometry. That is to be demonstrated. Okay, object detection. Again, I'm going to talk about photometry, honest I am, but you care about how we define what we're going to measure. So the detection will be near optimal for faint objects which look like the point spread function. So here's an example. This is some moderately, I don't know, this is an hour integration on Hypersupreme Cam, I think. So to translate that, that would be 120, something like 1 year depth on LSST if you allow for the added size of the mirror. HSC is on Subaru, it's an 8.2 meter, and LSST is a 6.5 meter. Okay, so what you see here is a cluster of galaxies. I've left the cosmic rays in. These red lines are the ghosts of cosmic rays. This is a stacked image. And the blue is the definition of what we mean by an object. And you'll see there are crosses that mark all the detections. So basically, the detection algorithm is to say, if there were a star centered on this pixel, would I be able to detect it above 5 sigma? Okay? If I could have detected, I know there's a star there, so I put down a little footprint, a little mask that says, I'm a star-sized object here. And then we merge those together. And that gets you not the faintest wings of stars, of galaxies. That's okay, I'll talk about that in a moment. But this is what defines what an object is. And if you look at this, this whole cluster is defined to be one object. And it's distinct from, say, this object over here. I don't know if you can see my mouse moving. I don't know how blue.
Robert, when you say pixel here, do you really mean pixel, or is this some kind of, have you gridded to subpixels?
Yeah, okay, no, this is resampled onto the sky. In fact, this track 9813 patch 44 tells you it's a coad. The pixel scale this has been regridded onto is very close to the native pixel scale, which is in this case 0.168 arc seconds. The best seeing we ever get is about 0.4, so maybe we could have gained a little bit. I believe that we're currently planning to resample the LSST data again onto the native grid of about 0.2 arc seconds. I will be pleasantly surprised if we have sampling problems down on the LSST camera. The median seeing is expected to be about 0.7, but I have no idea what it's really going to be.
But, you know, once a source is even moderately bright, you will know its location to much better than 0.2 arc seconds.
Of course, yes.
So maybe I'm just taking it too literally the way you phrased here. You ask each pixel if it's the location of a PSF. You're not putting locations, you're not restricting the objects to have locations on a 0.2 arc second grid.
No, I'm actually smoothing with the PSF, which defines a log likelihood image. I'm thresholding on the log likelihood image. Then I'm growing those detection regions, and that defines it. But that comes down to statistically what I described.
Is that all spelled out in one of those documents, or is that just the same Sloan? It's the Sloan procedure, basically.
Well, it's the maximum likelihood estimator for faint sources.
Okay.
I don't know if it's probably an LDM 151, and it's quite likely to be in the Bosch et al. Paper. There are a lot of algorithmic details in the Bosch et al. Paper, actually.
Okay.
I would recommend it as very interesting reading to anybody who's interested in LSST processing, because it really is about 1 year old DRP pipeline. We're doing better than that now, but that was the state of the art as of about a year ago, of our art at least. Can I go on? Any other questions?
That's
I'm
great,
happy
thanks.
to be interrupted. Go on. Okay. We will allow for correlations of the pixel as necessary. There are ways to deal with correlated noise, and it's pretty easy, pretty straightforward. So we will deal with that, both in terms of the detection filters and the threshold levels. Okay. You can look for more extended sources. You can put broader filter detection filters through. HSC experience implies we will not gain very much. We did this on Sloan and it really helped. I think it's just at the depths we're getting down to, most things are pretty well unresolved. But again, that's totally up in the air. Okay, now I would remind you that there are complex interactions between the sky estimation, the detection, the size of the objects, and what the deblenders do. And we are aware of these. I'm more than happy to discuss these, but I wasn't going to discuss them in this talk. It's a fascinating topic. I'd love to see you. Maybe if you're coming to the EVIL meeting in Tucson this summer, we can spend some time talking about it. But I'm leaving that off scope for this talk. Okay, astrometry. I promised I wouldn't talk about astrometry. John Gizas just dropped off, so maybe I don't have to. But you do need to know a centroid to measure a flux. So logically, and we don't actually quite do it this way. This is where the question of how you do things in multi-fit or in direct coads comes in. And again, I wasn't going to talk about that today. Logically, we will measure the properties of a coad. The centroid model for sources is a position plus a parallax proper motion. So that's 6 parameters. The instrumental color dependencies, that's coming from DCR, and it's coming from the SED coupling to the point spread function. For Kolmogorov seeing, that's lambda to the minus a fifth. For von Karman, it's a bit stronger chromatic term. But we will include that. If Gordon were on here or Schlegel, they'd be worrying about how we include really obscure SEDs in the PSF models. I'm aware of that issue. I haven't actually got to the bottom of that yet. We had thought about just letting you specify a couple of colors. I don't know how we're going to do that. But we will take out the color dependencies in the PSF model, so that automatically corrects not just the point sources actually, but anything you're modeling for the properties of the PSF and the DCR, differential chromatic subtraction, because LSST does not have an ADC, atmospheric dispersion correction. Okay. There's forced photometry on the difference images. I don't think we've ever spelt out, I should check, but I don't think we did, what centroid we would use. Naively, we would do this using the moving model from the coads. Now, I didn't put any really deep data in here, but at the depths that LSST goes to in 20 years, before you even start spreading deep drilling fields, these fields are moderately crowded in galaxies at high latitude before you start adding stars in. And I'm very nervous about doing really precise centroiding on individual epochs for faintish objects. Now, that's not a problem for difference imaging, but the trade-offs of how we deal with deblenders and centroiding and defining the positions of objects are not trivial. However, for things that are moving and are bright enough to be fitted not per epoch but over the complete ensemble, then we would use a moving model from the coads. The number of degrees of freedom lost by including the parallax and proper motion even for faint objects is very small. And as I'm going to make the case later, you really don't want to treat faint things that might be stars differently from faint things that you know are stars, because you don't know actually what's a star and what's a galaxy. I've got a few more numbers on why I think that's okay. So provisionally, I would plan to centroid everything as if it were a moving point source, with priors probably. We'll have to talk about priors on the parallaxes. What else was I going to say? And of course, centroiding galaxies is tricky because asymmetry in the galaxy profiles couples to asymmetries in the point spread function. So you have to be careful. Fortunately, people don't care as much about centroids of galaxies as they do the centroids of stars. Okay. The DPDD also promises forced photometry on direct images, and we will use the same centroids as we used for forced photometry on the difference images. So at least those will be on a consistent system. Okay. And indeed, you should be worried about how the deblender behaves doing forced photometry on direct images. Exactly what that means is something that we will see, and we will discover what the scientific yield from forced photometry on single epoch images is. I know there's concern in the community. People like Monet are very worried about losing information if you don't go back to individual images. So I think it's a trade-off we'll have to study in conjunction with you lot to come up with the optimal scientific way of dealing with this. But at the moment, anyway, we're doing forced photometry on the direct image. Okay. The DPDD states the centroids will be computed independently from each band for galaxies. I'm not allowed to say that the DPDD isn't perfect because Jelko told me not to. But here is a case that I think that this just slipped through. Nobody noticed that this doesn't make sense. The only way that this will matter is to the solar system people. We have to worry what we're going to do about things like comets, which may be where this came from. So I don't know the answer to that, but I don't think we want to be measuring galaxy fluxes about different centers and different bands. So, types of flux measurements. Lots of algorithms in the literature. I said most of this already. It's really valuable to use an algorithm where you can that can be applied to all objects. And in fact, we certainly plan to apply all algorithms to all objects, but not always necessarily. So in forced per epoch on a 30-second exposure, we won't fit Sursich profiles to the galaxies because they're going to be the same on each epoch and you get very much higher signal to noise. And we reserve the right to not use some extremely expensive algorithms on all objects. I don't think this is likely to be an issue in practice, but it is a project right to not do that. Okay. And then let me just talk a little bit about absolute and relative photometry. So there are fundamental differences here between the relative and absolute photometry, where relative means between objects nearby on the sky, and absolute I'm using here not to mean relative to CalSpec standards, but so that I can quote the flux of the object, and that means something when I compare it to an object that's 30 degrees away. Okay. So relative flux measurements don't care about the instrumental throughput, providing it's constant over the field. I will come back to that. And uniform layers of cloud, whereas, of course, the absolute photometry does. I don't think this is an issue because everybody now calibrates locally relative to Sloan. Well, you shouldn't use Sloan anymore. You should use Pan-STARRS, which has been calibrated and improved on Sloan. In the south, DARES, SMASH, I guess, and in particular, Gaia. Gaia gives us absolute photometry across the sky down to about 20th magnitude. They're not all that accurate at the faint ends, and doesn't provide U and Y photometry. I think we can extrapolate that using models from the Gaia RP-BP data. We have not demonstrated that. Okay, relative flux measurements for objects of the same shape are unaffected by seeing variation. So the easiest case of that is when the shape is a delta function, that if you make a relative measurement between different stars in the same field, you get the delta magnitude. If you know how bright one is, you know how bright the other one is. That's how we do stellar photometry. But it's also true for galaxies. Okay. If you're doing relative flux measurements for the same object at constant seeing, you don't need to measure the total flux. That's true for stars as well. You don't typically measure the flux out to 2 arc minutes, though you can trace the wings of stars out to 2 arc minutes. You measure a much smaller region and you apply a curve of growth correction. Or more likely, you make the same flux measurement on the standard stars. You know how bright the star is. You know how much brighter the star is, fainter than the standard star, and you're good to go. So relative measurements are great. Now, the relative flux measurements of the same object at constant seeing is incredibly important for photometric redshifts, where you don't need to get the total flux of the object. You only need to get the flux of a well-defined part of the object. Because if you measure the photo Z of 1 square kiloparsec of a galaxy, it's the same as the photo Z of a different square kiloparsec. We can't resolve the rotation curves with photometric redshift. So that doesn't mean that you can do SED fitting that way. It won't mean what you think it does. But you can get a correct photometric redshift by concentrating on the bulge or concentrating on the whole galaxy. Okay? So it's tricky to use, for example, Gaia, and I will talk about that in a moment. But just remember that basically local standards make things easier, and that's what we're planning to do. Okay, so point sources. We will measure, in fact, we're already measuring, aperture fluxes with a range of aperture sizes, logarithmically spaced, which means you get roughly constant signal to noise per aperture for some particular profile. You don't really get constant signal to noise, but sort of. And it also means that they're nested, so you can ask about the total flux within either an annular aperture or a total within an ellipse. We're using elliptic aperture. Okay, these will be corrected to canonical seeing, and the DPDD says 0.9 arc seconds. I'm worried about this. I'll come back to that in a little bit. And we will measure PSF fluxes. So those are the two fundamental things we do for point sources. And of course, the former are optimal for bright sources, the latter are optimal for faint sources, where the difference is whether the photon noise from the object or the photon noise from the sky back, and that dominates. Okay. This is an example where survey astronomy is very different from going out to a small telescope and taking your own data, because LSST is responsible for putting the count measurements onto a standard system. So we are responsible for handling the PSF and aperture flux, aperture corrections, and tying us down to a well-defined aperture. So these aperture fluxes, as I mentioned up here, define a curve of growth. But you should not need to look at that curve of growth and process it yourself. It's useful if you want to know about wings of stars, or more likely galaxies. I'll come back to them in a moment. But it's not necessary to use that for your own calibration. So we will deal with the variation of the aperture corrections across the field as the seeing changes. And that means you shouldn't worry that I said the aperture measures are PSF normalized. That's not a normal thing to do. It means they're not quite direct measurements of what you think they're measuring, but they're more useful. Okay. Okay, galaxy fluxes. So relevant flux measurements are point spread function fits, see above. Model fits. So we have said in the DPDD that we will fit a bulge and a disk in each band. So that's a combination of PSF convolved exponential Devote components at fixed ellipticity. Okay, and we promised 200, I think, samples. So that's a maximum likelihood fit essentially, and you might want to know what the likelihood, the shape of the likelihood fit surface is, rather than just getting the mode. This was designed when it looked as if state-of-the-art for shape was going to be something like Lance Miller's lens fit code. I don't believe that's true anymore. I'm not a weak lensing expert. There are too many scary people who do that, but I do follow the field. It looks to me as if with the advent of Metacal and possibly the BFD stuff that Gary Bernstein and Bob Armstrong have been pushing, Bayesian shape measurements, we will not be probably measuring the shapes of the galaxy fits. If that's the case, the community may tell us we don't need these 200 samples, but that's out of scope for the project to decide. But we will negotiate. It's moderately expensive. Okay. Now the choice of priors to interpret these fluxes, I'm measuring a likelihood, I want a posterior, are complicated. Even if we forget about the Hogg-Turner thing, which I don't really fully understand, but it's related to the definition of sky, I think, which is the divergence of the posterior probability. The priors are complicated because priors influence depends on signal to noise as well as redshift. So this is not a pure scientific case. It's a nasty, subtle thing. So if we use priors, that breaks my claim that relative flux measurements, even for objects of the same shape, are unaffected by seeing variations, because the relative importance of the priors matters. The influence of the priors matters. Okay? So I think it's more likely, and this is based partly on experience by people like LensFit, like Lance, that we will fit the amplitudes in each band rather than the shapes of the components. Now, that is a very general assumption about galaxy photometry and is, I think, necessary when you're talking about the blenders, certainly the way I've ever thought about them. And Peter will say more about this. But people worry about color gradients in galaxies. But most color gradients that people are thinking about in galaxies are really multiple components with well-defined colors. For example, a red bulge and a blue disk. This is not strictly true. It's not true when there's dust. It's not true when you have a metallicity gradient in an elliptical galaxy, so you're bluer in the outer parts. But to leading order, I think it's true that you can think of color gradients in galaxies being combinations of components with well-defined colors. That makes the whole question of what you do about seeing corrections tractable. It makes a deblender tractable. So I would be extremely surprised if the modeling that we do doesn't, in fact, fit, as it were, two surface components with amplitudes freed up between the bands, rather than freeing up the scale lengths or something like that between the bands. Okay. And this is a parenthetical note that model fit magnitudes work incredibly well for point sources. This is really embarrassing, actually, because it shouldn't be true. In Sloan, the model fits are actually slightly tighter than the point spread function fits for stars. I don't understand why. But a 3 millimag offset measured in the HSC coads means that these models that we're making, we're actually using the Sloan swindle. We're not even doing something as principled as I described here at the moment. Produce really very good fluxes for stars. And that's really great. It means you can say, this is the flux of this object before you run the star-galaxy separator. That's something that I believe was a real bonus in SDSS. I think it'll be
Robert?
a bonus. Yeah.
Just to interject, how well does that work in crowded fields?
That's a question about deblenders.
Yes.
Yeah.
So the same model fit
It
photometry.
can't work as well. It depends on what priors you put on faint objects, at least partly. And we will certainly measure the PSF fluxes. And if you know you're interested in stars, you might as well use them. They shouldn't be worse. They've got to be better where you've got lots of things in the wings. I totally agree.
Okay,
But I was quoting numbers in things like Cosmos down to 22nd, 23rd magnitude, where these numbers are, I think it was 22nd, where these 3 millimeg scatter comes from. It's a very surprising result to me that the extra degrees of freedom don't really mess you up. But I think it's because you've marginalized over the really ill-determined shape of that model because it doesn't change the flux at all. Okay, so it's very flattened, but its RE is 10 to the minus 2, so who cares? And that's actually why the Sloan Star Galaxy Separator was built on the difference between the model and the PSF flux, because that tells you what you want to know about the profiles, whereas the likelihoods tell you something about how little you understand the noise and things like that. So you're quite right. If you're thinking about stellar photometry, you know there are no galaxies, then you might as well use stars. But remember, there are 1 million galaxies per square degree down to the depths we're going to. And that's how many, that's not, the stars don't massively outnumber the galaxies.
Well,
But
I was thinking
22nd,
in the galactic plane, that may not be true.
It's not true, but there are still a lot of galaxies, right?
Sure.
So you can't assume everything is a star any longer. And I'm not going to talk about crowded field photometry because I'm not allowed to. And I think it would get us very far off topic. It's a fascinating question. How you can manipulate the priors on your models to reduce to almost guaranteed to be star in the case where you've got almost all stars. But if you've got something with a lot of evidence that it's not a star, you allow it not to be. And that's the sort of thing that Peter and I have been talking about. So please come back and ask those questions. I would happy to be in the conversation, but I've got other things to talk to you about today.
Sure.
Sorry.
Thank you.
Okay, shape measurements. Okay, no weak lensing. However, unlike SDSS, we are going to measure galaxy photometry using elliptical isophotes, not isophotal photometry, don't worry. So we need to define which ellipse that is. The current proposal is to use these adaptive moments, which came out of this paper by Gary Bernstein and Mike Jarvis 15 years ago. They are reasonably robust and the limit of not very high signal to noise. We're actually going to correct those so that small objects are round. Exactly how this works turns out to be trickier than it was when I first invented this proposal, but we need to do something. So we want a measurement that's round for anything where it doesn't matter. But if we've got lots of evidence that this galaxy has a flattening ratio of 2 to 1, and it's well resolved, you want to do the photometry correctly on that. You need isophotal magnitudes. Sorry, I need fluxes based on elliptical isophotes, and this is how we're going to do it. That's just a technical detail. Okay, and again, priors matter. So, galaxy fluxes. So first of all, we're going to measure what now turn out to be elliptical aperture fluxes. They're the same apertures as I measured for stars. The previous slide said, I worry about making sure these work well for stars. I'm not all that worried about that, but it has to be demonstrated. The data will be normalized to canonical seeing. Okay. We will measure both Crone and Petrosian elliptical radii. So we will measure the flux contained within the radius of the canonical band. This is just like SDSS. We'll probably use I band. We could use Z band. Again, that's a question for our scientific collaborators. We will report the radii containing 50 and 90% of the flux. That's the R50, R90 values that you're probably familiar with. I should warn you, the Crone radius is hard to measure for very faint sources. It's very badly defined. Most approaches, including if you read the source code, Emmanuel Bertin's approach in S-extractor for mag auto, in fact reduce to an isofocal radius. This is not good. It's one reason why Crone radii are really not very satisfactory. A, I wrote the code, and B, people are very familiar with them. We will provide them. We'll also provide Petrosian fluxes. I believe that the experience has been that these reasonably complicated model fluxes are at least as good as the Crone and Petrosian fluxes. It's certainly true for bright isolated galaxies. As Rachel was about to ask, is that true in clusters of galaxies? That's a very good question. It's one of the cases that models, more constrained models, possibly fit simultaneously in the deblender, may well give you better colors. Colors matter for photometric redshift. So I don't know the answer, but you have to pay attention. Okay, galaxy colors. So we have said we will measure standard colors, it may be spelt wrong in the DPDD, matched to a standard PSF. And as we point out, these are seeing insensitive. We propose that we match the 75th percentile of the seeing and guess that will be 0.9 arc seconds. Now, after 10 years, that distribution will be tight at any point in the sky, I think. Leaves me well, I mean, the distribution of seeing at a particular point, we will have outliers, so the 75th percentile will not vary much. It's going to be a function of position, it's going to be a function of declination, seeing scales of the RMS to the 0.6. So I'm really quite worried about how we define this 75th percentile. The details of how we do this are tricky. I don't think anybody on project has thought through this yet. We should go and talk to people like kids. Kids normalize all their seeing. I don't remember what they did for this in the end. Conrad is, I think, the person to talk to. Okay, so the only safe way to measure a flux that can be used for colors is to measure the seeing in all the bands. That's what we said we would do in the DPDD. If the models are good enough, the model flux is the total flux in the object, and that's independent of the seeing. Now, if the models are not good, that's not true. So there's a trade-off between how well the models fit so they recover the total flux in the object, so it's seeing independent, and how much you can degrade everything to 5 arc second seeing and measure the fluxes. And which of those yield better science is not clear to me. Or more likely, you would do a certain amount of normalization and a certain amount of model fitting. But the question of what the optimal colors are for, in particular, photometric redshifts is, I think, open. Now, if you want galaxy colors for measuring the star formation history of the universe, then you definitely want a total color, a total flux. Total flux is very hard to measure for galaxies because you don't see any light in the outer part, and you have to worry about what happens to the wings, you have to worry about the intracluster light, you have to worry about the sky subtraction. Okay, so when you're doing photometric redshifts, you can also choose a weighting when calculating the flux. For example, we could upweight the bulge because we know it has a strong 4,000 angstrom break. So though it's got less signal to noise than the overall object, but not that much because it's higher surface brightness, we might, again, as a project, not as the project, want to upweight the bulge. And in fact, there are people like Kevin Bundy who will claim that the way I did this by mistake in SDSS upweighted the fluxes of the bulges, and that's one reason why the photo Zs were better than one might have been led to expect. Okay. Of course, if you change your definition of how you measure the galaxy flux, you have to tell the people who train the photo Z codes, because I've just changed P of Z. I've moved galaxies around in color space. Caveat emptor. Okay, so photometric calibration. So I said we could use, for example, Gaia to provide a photometric 0 point, but it's not as easy as that, regrettably. Snivel complain. So what do I mean? What I mean is that when we measure a certain number of counts in a band B, and I guess I may or may not have written down that B stood for band, that's the sort of thing I would add before I put the slides out permanently. We were talking about it before the talk, is some constant which involves C and H bar times an integral overall for frequent overall wavelengths of F nu, that's the SED of the object, the sensitivity, the transmission function of the atmosphere, the transmission function of the system, including the filter, and then we're counting photons, so it's d lambda over lambda. Okay? So to draw conclusions about F nu, which is what we care about, from the counts, we need to understand both the transmission of the atmosphere as a function of wavelength and time, and the system as a function of wavelength and time. So First of all, you have to worry about the ISR, the instrument of signature removal. We'll do all the standard things. We'll fix a nonlinearity as well as is known. We will fix problems in the ADCs. If you've been reading Archive this last week, there are exciting problems due to in ADCs, where ADC now stands for analog digital converter, not atmospheric dispersion corrector, sorry. We will apply flat fielding. We'll correct some level of pixel size variations. That's hard, actually. But we will not correct for the QE variations, because you can't. Because the QE variations are a function of wavelength, and they only enter the counts after you've integrated over the Fmu, over the SED. So you can't do classic flat fielding, because that depends, as we all know, on the SED of the source. That's normally only a problem. Well, let me keep going. Okay, so we will use monochromatic illumination in the flat field screen to measure the flat field as a function of wavelength. Now, those of you who have done this on wide field images will be thinking, but. That's really tricky because of ghosting and scattered light and things like that. We have a thing called a collimated beam projector, the CBP, also known as the Stubbs machine, to deal with that. I'm not going to talk about how, but we have a cunning scheme of basically generating monochromatic star fields and dithering those around. I believe that will work. Okay, so how about the telescopes and the filters? Well, it turns out that the CBP, which puts monochromatic spots onto the focal plane, lets us measure the system throughput at a finite number of points. We can also take the filter out of the beam. That lets us measure the filter. So basically, we know the full system throughput is a function of wavelength at every point in the focal plane. That's good. Congratulations. To be demonstrated how well it works. So how about the atmosphere? The atmosphere is a problem in three ways. It messes up the seeing. I'm not going to talk about it. It causes a bright background. That's a problem. I'll say a little bit more about that in a moment. And of course, it absorbs and scatters light out of the beam, and that looks like it's an obscuration. We get less light than we should have done into the point source. So the background light has a spectrum that varies with time. Depends on the phase of the moon, depends on the solar activity. I guess it also depends on the amount of aerosol. Our knowledge of the CCD's flat response, because we have monochromatic flats, means that if I know the color of the sky, I can flat field the data to flat field the sky optimally. That's one of the reasons why it's hard to do global sky subtraction on wide field images, because all the chips have slightly different chromatic responses. We get a chance to deal with that. After doing that, we can, after sky subtraction, which is going to be done on the scale at least of the camera, 10 degrees, we can reflatten the sky, the data now without the sky, to a flat spectrum source, maybe a G-star source. Jim Gunn says G-star because that's closer to reality. I don't think it matters. So what about the obscuration? The atmosphere, the bright part of the atmosphere are dealt with, removed, and now we have to deal with obscuration. So I would remind you, here's a picture of the atmosphere, and I'm afraid I forget who made this. If they're on the phone, let me know and I'll give you a credit. That there are components from the water, the oxygen, there is some from the nitrogen, it's at a very low level, the ozone, the radio scattering, and the aerosol terms. And these are all one parameters, except the aerosol is two. It's an optical depth and a slope, because the slope of this term, this yellow, ugly yellowish term, depends on the size distribution of particles in the atmosphere. It depends on where the wind is coming from, whether we're getting deserts or salt, or which volcano has gone off recently, all those sorts of things. It varies on quite short timescales when the wind changes. This spectrum is a simulated spectrum. There are codes. The American one is called ModTrans. It looks as if it's written in Fortran 66 by the way you configure it. There's a European one called LibRadTrans, which is, I think, equivalent, which give you high-resolution models of the atmosphere and deal with the fact that these lines are actually saturated. Some of them are saturated, some of them aren't. So you can't just assume that things scale as air mass to the 1 or air mass to the 0.5. They scale as in nasty ways. And some of them don't scale at all because they're saturated at zenith, so you just can't regress them out. So we also have a 1.3 meter telescope called the Auxiliary Telescope. It used to be called Calypso. Eli Rykov wants to call it the oxtail, as in soup. I don't think he's going to win that battle. It has an R of order 100 spectrograph with a simple optical design which is wedged and often tilted and things like that. So there's no ghost light near to the primary image. This is a spectrophotometric machine. It's using an LSST chip, so we've got good red response. So my current plan is to use Gaia RP-BP spectroscopy of stars in the range 6 to 8 mag, and to choose those stars with simple spectra to constrain the atmospheric models. That's great if it works. Just to remind you, this is, I think, the only Gaia BPRP photometry that's been released so far. These are spectra, 2D spectra from commissioning in Gaia, and this is not centered because they got something wrong. They're going to fix that. And these are the extracted spectra. And just to remind you, this thing, V1293, which is the red star, is at 6.7 magnitude. It's a variable, of course. HD 207, which is an A star, A3 star, is this blue thing. So these are resolution, not very good spectra. They're spectrophotometry. They're tied to CalSpec standards. They're taken from above the atmosphere, and they're rigid across the sky, because as normally with Gaia, you're comparing photometry from objects over here and objects over there. So I believe these will give us spectra which can be compared with the data coming out of the auxiliary telescope. We will know more on the 26th of April 2018. GDR2 occurs on the 25th of April. Jelko doesn't think we're going to know very much more, but given epsilon greater than 0, we will know more. Corinne Baylor-Jones, who's responsible for fitting the data to Gaia, tells me that he believes that their model fits will be sufficient statistics for the data, which means that the spectral fits that they are doing are claimed to be sufficiently accurate for a simple range of stars, A stars, to be good enough to specify the atmospheric transmission. We will find out. Okay, so finally, we now know the atmospheric transmission. We know the system throughput as a function of time. If only we knew the SED, F sub nu, we'd know how to interpret the counts, because I could do that integral. Every observation of each object has a different combination, of course, this term here, S atmosphere, S cis. So the current plan is to define and assign SED to every cell in UGRIZY space. And that tells me what the F nu is. So I can then, for that object, on that assumption, I can interpret those counts in terms of that F nu, and I can tell you what I've done. That means I've backed out the varying atmospheric and filtered transmissions. And remember, the filters may or may not be as uniform as one would like, and the response of the chips is probably not as uniform as one may like, and there may well be more than one type of chip in the focal plane. So you certainly shouldn't assume that there is one filter curve that applies to LSST for all the time, even before the mirrors degrade. Okay, if I guessed that SED correctly, I'm done. I've done everything that'll get us photometry allowing for the atmospheric transmission. If I'm wrong, we're not yet dead, because if the sensitivity doesn't vary on the scale of the object, I can repeat that SED correction at the database level. If I have a measurement of counts in the single epoch photometry, I know what the properties of the two S functions are. Actually, the product is all I care about. So I can give you a, what do you call them? There's a word, catalog procedure in JCL. Basically, a database function that lets you say, my SED is, it looks like this. It's a supernova type 217BK at redshift 5.9. So what's its photometry? And of course, it'd be bright if you care at that sort of redshift anyway. So there's enough information for you to back out my assumption about the SED and redo the photometry. That requires that the object's per epoch flux is well defined, which means again that the per epoch deblending is reliable. Now, that's actually okay for transients like 1As, because we can measure their flux in the difference image. Now, if you follow 1A photometry, you'll know that people like Pierre Astier say, no, 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 we don't do difference imaging, we do forward modeling. But that's just a way of saying the same thing, describing which image it is you're subtracting off. So that's also just fine. So take that as a shorthand rather than my ignoring the experience of the CFHT supernova group. Okay. It's also no problem for sources that don't vary, as we will propagate the average value with appropriate weights for every object on the coad through the system in just the same way as we propagate the appropriate point spread function for that object on the coad. I'm more worried about things that vary and don't show up interestingly. Well, I'd have to think about it. AGN or something like that, where I want to know the total flux. It's very crowded. I just don't know how to solve that problem without a reliable deblender. I think there are no important cases. Joko just asked me how you find variability of faint objects. Again, this is a question for the stellar people there. But generally speaking, you want to know we can find the variability from the difference imaging. I'm more worried about how we calibrate the overall flux level so you can get the flux of the Cepheids, you can measure W triple prime, whatever you're going to do. I haven't thought through that. But the fundamental objection here is that in very crowded fields, when I'm worrying about galaxies, and most of these examples are all stars, because really stars vary, there are some technical issues. I think they're not the end of the world. Okay, so
sorry.
Yeah.
I'm just not sure I understood. You're saying that this is not an issue for supernova type 1a because you can do it in difference imaging, but for something like an AGN, it becomes an issue again because there is an intrinsic variability of the transient in the templates?
I'm worried. No, it's not that problem. I'm worried about how you're going to measure the total flux of the object. I can measure the varying part.
Okay.
For AGN, which is what I thought of it, I don't think it matters because nobody terribly cares how bright they are in gory detail. If you're worried about variables, you're trying to do RLRI in some external galaxy. That's a bit of a push. Well, we can probably do it, but you know what I mean. Then you do care about the overall flux.
I see.
And then I have to think about how we're going to do it without going back to the pixels if I get the SED wrong. Now, of course, variables change their SED as by phase because they get brighter and redder, but that's second order, so maybe it's not an issue. I'm just trying to raise some questions that if I were on the other side of this microphone, I would be worrying about. And that's my last. I give you 2 questions to ask and ask you questions. 2 minutes to ask questions.
Actually, there is a question by Gordon Richel through Fear Marshall, which is about the measurement on AGM, mid flux, and community. Phil, can you ask this? I'm not sure.
Yeah, actually, that was just a note for everybody. So Gordon actually asked about measurements of AGN mean flux on community just this week. And there's some interesting back and forth about how to do it and whether the DPDD needs editing. It's worth a look.
Yeah, the whole question of how you phase templates is nasty, actually. You can imagine logically taking all your coads, then subtracting all the difference images to phase them back to epoch 0, but then you add all the noise back in. So how you do that is tricky. I don't know the answer. And here's presumably, and opening the question, he could have said the same thing about RLRO.
Yeah, I think he was also worrying about the galaxy flux as an implement to the
Well, I should read it. The galaxies are, you have to be very careful. In fact, I was discussing some of this with Neil Brandt in Princeton. When was that, Neil? Last week. It's hard.
Are there any other questions? Sorry.
I have a very quick one. I thought it was cool that you're implementing this, learn the SED and making good use of the filter transmission curves varying, the filters being different, the properties of the chips. Do you have some sense of how much variation there really will be? I mean, are we going to get significantly improved photo-Zs as a result of this analysis?
I can give you, let me think. The effects come in below around, for decent systems, below around 1%. For a hypersimple cam, where we have gradients in the AR coats of some of the chips, which was, I think, seen for a while in our chips, the LSST chips. I don't know whether it currently is in the blue, and I don't know how good the filters will be. I don't know how big these effects will be, but I'm predicting we'll have trouble below around 1%. Now, the Photo Z people who I used to talk to said, I don't care about precision below 5%, but they've changed their minds. So I'm assuming that we care about even the Galaxy photometry colors as well as we can measure them. And if below about 1%, it begins to matter. One of the issues in all this game is, I think I've convinced people that we can do this for stars. In fact, you can either measure it directly off the data, or it doesn't matter for stars. In the sense, well, it doesn't matter. That turns out to be true. There's still some dispute in the bluer bands as to how well self-consistently we can measure the colors of galaxies. And that's very closely related to the question of how much these corrections matter for galaxies. So I don't know the answer to that.
Cool, thanks.
I will say one more thing about that. But some of the degeneracies that you see in Photo Z codes, where you get multiple photometric redshifts at the same color cell, don't matter here, because the degeneracies come because the SEDs are similar, but it's 4000 break, not the Lyman break. And that doesn't matter for what I'm doing here. Here I just require that the SED be similar, not that the astrophysics be similar.
Okay, any other questions? I don't see anything on the chat. Let me check on Slack. I don't see anything on Slack. Excellent, and we're at the top of the hour. So, brilliant, we did it. So the notes were being scribbled away by myself during the talk. So curb your enthusiasm and your expectations. I will go over the recording and see if I can improve them. They will be available. I will send out an email. You have the link already, and I will make them available on community as usual. As you probably recall, we have the collection of all the talks, videos, slides, all the material available for each one of the talk is on lsst.org/scientists, which incidentally is also the webpage that we're asking for feedback from you and your science collaboration. So please remember that I did send you a form to collect feedback about these pages because we're trying to improve them. I don't have the calendar on hand, but there is another talk scheduled for sometimes towards the end of next month. There is the calendar, which is a Google Calendar, so you can sign up for it and get notifications. Thank you so much, Robert. This was excellent. And we will continue the discussion on community. So please, Robert, follow it so that if we ask you a question, you can interact with us. That way, we will post the minutes, the video, and all of that on a community dedicated page so that we can continue talking.
Yeah, I'm always happy to be pinged. I mean, I may tell you to go to community, but if you're not getting responses that you think you need, you're more than welcome to send me grumpy email, which I will ignore. But
brilliant. Thank you. All right. Thanks, everybody. Thank you very much. Bye-bye.